In this video, we're going to look at how our first perspective applies to simple harmonic motion. As you can see, that's going to be kinematics. Now, the one thing that I can't emphasize enough, and that is that you cannot use the equations of motion that we derived earlier in the year, because that is for straight lines. And with simple harmonic motion, we're constantly moving between two extremes, and we're repeating the same path again and again. And it's just not going to work here. Part of the problem is not only the path, but another part of the problem is that the force is a linear force, which means it's not constant. It's increasing or decreasing linearly with time. So the force, it's constantly getting bigger or smaller. So by implication, according to Newton's second law, the acceleration is also going to increase and decrease with time. So we're going to have to develop a brand new set of equations of motion. And that's actually quite easy to do. Now, the method that I'm going to show you here for understanding the model, it doesn't actually tell us why it has to be that way. But understanding those types of details are well beyond the scope of a course like this. So what we're going to do is we're going to imagine that we have a bottle of time sitting on a Lazy Susan. And so this disc represents that Lazy Susan, and we're looking down on it from above. It's sitting on a table. And so the bottle I'm referring to is it's sitting right here. Okay, so right here is my bottle. Now, if I get down to eye level with the bottle, what I see is a disc, which is no longer a disc, but it's just like a straight line, and sitting on there is my bottle of time. Okay, and so if I draw a straight line from here to here, then you can see that the position of the bottle in time, it's going to oscillate. If we ignore depth perception, it's going to oscillate from left to right to left to right to left to right. Okay, so this bottle is going to be moving between two extremes. Now, in the first video, we looked at a key term, which was amplitude. And the amplitude is the point of maximum displacement from the equilibrium position. And so when you look at the Lazy Susan from above, you can see that the bottle is always going to have to be moving between negative A and positive A. It's always going to be between these 2 points here and here. So we're just going to label this minus A, and this is going to be plus A. And of course, right here represents our equilibrium position. So if I want to know what the position of this bottle is on the x-axis, then I'm going to have to do a little bit of trigonometry here. And you can see that I have formed a right triangle here. Okay, now the radius is r. All right, and that's actually a position vector. Our position is located right here. This is our position. But we are located in a two-dimensional space, and so r is how we represent that two-dimensional space. It also so happens to be that r is the amplitude, so we could say that r is equal to a. Alright, now this is our angle theta here. So if you want to determine what is the position, the horizontal position, all you need to do is r cosine of theta, and that will give us our position in x. That's going to give us this, from the equilibrium position to where the object is located. So x is equal to r cosine theta. Now, part of our problem here is that we have position as a function of angular position, which is okay, but oftentimes we don't know anything about the angular position. We need to determine what the angular position is at some point in time. So for that, we're going to go to our rotational equations. And what we had in rotation is that theta is equal to omega times t. Now, don't let that confuse you. It's really quite simple. It's really just like, saying, hey, if I'm driving at 55 miles per hour for 2 hours, how far did I drive? Oh, well, that's 110 miles. And that comes from d is equal to v times t. So you can see the similarity here. Theta is the position, omega is the velocity, and of course t is time. So we're going to substitute omega t in for theta, and we get r cosine omega t. And that is almost the equation of motion that we would use. The only other substitution we have to make is that r, we want to put that in terms of the amplitude, and since r is equal to a, we're going to say x is equal to a cosine omega t. And that is our first equation of motion. Now, this is not a calculus-based course, so it's not going to be so easy to derive or come up with the velocity function, so I'm just going to give it to you. But if you have had calculus, or at least some calculus, then you probably already know that the velocity is going to be the derivative of the position with respect to time. So for us, velocity is equal to minus omega a sine omega t. Now there's a couple things I want to point out about this expression. The first is that this omega a, that really just represents V maximum. Okay? Now, why do I say that that represents V max? Well, because if you look at sine omega t, this can never be greater than 1. It's always going to be less than or equal to 1. So basically what that means is sine omega t is a scaling factor. It's going to tell us that if the maximum velocity that we could measure at the equilibrium position is 2 meters per second, then the velocity is always going to be between plus 2 and minus 2. And if I had a velocity of 0.5, then that means I have 25% of what I could have. All right, so getting back to this omega a, if we go back to rotation for just a minute, we had a bridge equation. And that bridge equation was V is equal to R omega. So in this case, we know that R is equal to A, which would give us V is equal to A omega. And so this is consistent with what we learned back in rotation. We're just basically setting up a bridge equation here, and we're relating that to simple harmonic motion instead of rotation. But it is related to rotation through this diagram, and that's the key. Okay, so our equation of motion for velocity, we get V is equal to minus omega A sine of omega t. All right, now there's one more equation, and that's acceleration. And we're not going to do a whole lot with acceleration, but just for the sake of completeness, we're going to say that A is equal to, and again, this would have to be a derivative. You would have to use calculus to get this, but A is equal to minus omega squared A cosine of omega t. And that's going to be the last of our fundamental equations of motion in simple harmonic motion. The very last thing I need to mention is that this omega t that we have here, in all cases, the angle theta or omega t, this must be in radians. You cannot have it in degrees. It has to be in radians. Okay, so in the next video, we will take a look at some examples of kinematics in simple harmonic motion.